Assalamu alaikum warahmatullah. Welcome to this lecture number 7 of our subject mechanical vibrations. And today we are going to look into some advanced topics related to the Laplace transformation. So we are going to discuss what the transfer function is, uh, and what is how we can use the MATLAB to solve the partial fractions, because you guys know that partial fraction solution can be quite lengthy, and obviously our concern in this subject is the mechanical vibrations, not to discuss how to solve the partial fraction. So we will use the MATLAB to do it for us, to reduce the time, and then we will use the Laplace transformation in the MATLAB to determine the total response of a system, that is the steady state and the transient response. And then lastly, we'll study the we'll perform the frequency domain analysis of the system, that is using the sinusoidal transfer function. So we know that the transfer function and the Laplace transformation, we have a complex variable s that is equals to gamma plus iota omega. So this part tells about the steady state response of a system. So there's a sub transfer function that specifically deals with iota omega. So that transfer function tells us only about the steady state part of our solution. So if we have a total solution like this, that we have some transient part, and then we have some kind of steady state part. So whatever the vibration we have here, so that transfer function, sinusoidal transfer function, is going to discuss this part where we have the steady state condition. Unlike, it's not concerned with this region. So that was a brief intro of this lecture. So now we will formally start with what are the transfer functions. So let's start with the transfer function now. Mathematically, transfer function, again, it's a part of Laplace transformation. So and because of that, it is applicable for the linear system, time invariant differential equation system. And what are these, we have discussed in the first lecture. So again, refer to that. What are the linear system, what do we mean by the time invariant system? So Laplace transformation is specific for those systems, even if the system is non-linear. So what we do, we linearize that system and then apply the Laplace transformation. So, and since transfer function is the part of the Laplace transformation, so it is applicable only in the linear systems and the time invariant system. But mathematically, the transfer function is simply a ratio between, let's say we call transfer function to be function g of s. It is a ratio between Laplace transformed output of a system divided by Laplace transform input of the system. So what do we mean here? So let's say you have a system with a mass spring damper system. Let's say you have a spring here, you have a damper here, and they both are connected to a mass. uh, so they both are connected to the mass. uh, if you apply a certain force onto that mass, and because of that the mass undergoes some kind of displacement, so it means this was your input force and this is the output. And how much excitation or how much displacement will occur in your system because of the applied load. So it will be g of s will become a Laplace transform of f of t divided by the Laplace transformation of sorry, it's x of t divided by f of t. So Laplace transformation of output divided by Laplace transformation of input. That's all what the transfer function is. So if we make the equation of motion for this one, so I'm going to directly write this one. So it will become mx double dot plus bx dot plus kx, and since it's not, it's a force vibration, so it will be f of t. And if you take the Laplace transformation of all of these, I have shown the calculation in the last lecture, so you can refer that. I'm going to write it directly, so it will become ms square plus bs plus k whole into x of s equals to f of s. Now the Laplace transform will be output over input, so it should be x of s divided by f of s, and it will become 1 over ms square plus bs plus k. So this is the transfer function of this system that we have just seen. So what it tells, the transfer function is really important. It's kind of a mathematical model expressing the differential equation that relate the output and the input variables. So the first we have seen, it relates output and input and input of the system. It's a property of the system itself. It doesn't concern with the magnitude and the nature of the input and driving function. It is a property of a system itself. So it it's kind of a certain property that if you give the input value, it will tell you the output value. So if you know the transfer function of any system, you can calculate its response with respect to any input excitation. So it's a system property, and you can call it, it's unrelated to magnitude and nature of excitation. So thirdly, uh, it does not provide, maybe that's the case that multiple or different systems have the same transfer function. So it only concerns with the relationship between the output and input. It doesn't concern with the physical nature or structure of the system. So maybe you have an electrical system and you have a mechanical system, and they both have the same transfer function. So a same transfer function doesn't mean that the systems are same. It means their behavior to the input excitation is same. It does not provide information about the physical structure of the system. And lastly, and as I've mentioned, that the multiple systems may have the same transfer function, so it's not concerned with the physical structure of the system. Lastly, if, if let's say you don't have the transfer function of any system, you can determine it experimentally. Let's say you have a mass spring damper system, and you know the mass, you know the k value, you know the c value. Just give any known force, maybe sinusoidal, maybe impulse, or you can say unit impulse force or step force, and then measure its output. So now you know the input, you know the output, you can take out their ratio, and that will be the transfer function of your system. So if you don't know the transfer function of any system, you can determine it experimentally, like this one. So that's for the brief introduction of transfer system or transfer function and how it works. uh, Secondly, what we are going to discuss is the partial fractions. Now we are going to use it again and again. So we are not going to solve the whole equation itself. We are going to separate the outputs and inputs and take the ratio, and then that ratio will help us to determine the the system's behavior. Then next is partial fraction using the MATLAB. You can see. So as we have seen in the last lecture that when we are using the Laplace transformation, it converts the differential equation to the into the algebraic equation. And when you're taking the ratio between the output and inputs, obviously you will have some kind of complex fractions, and then you have to simplify that rational fraction into the simple fractions. And for that you need to use the technique of partial fraction, which is quite hefty or lengthsome if we do it manually. And since our concern is only the mechanical vibration, to study the vibration of any system, so we are going to reduce this task using the MATLAB. So let's suppose what happens. Let's suppose you have first of all I will explain it here. Then we will use the MATLAB how to do it. And I hope you guys have the MATLAB. If you don't have, you can just let me know. We will I will sort you out how you can use it. Secondly, yeah, let's suppose you have a Laplace transfer function, and that is output y of s divided by the input u of s equals to 25 divided by s square plus 4s plus 25. So obviously this is the numerator and that's the denominator, because we have to explain to the MATLAB what we are trying to get from the MATLAB. So that's the numerator and that's the denominator. So you will explain MATLAB, okay, numerator, and it works with the power of these exponent values of this complex variable. So we'll just write numerator equals 25 means it always works with 0 1 2 3 4, and you as you have the more entries into your matrix, then you will have the higher power in the numerator or the denominator, whatever you're defining. 25 means, so there's just a constant value. For the denominator you will explain it as 1, which is the constant value of the highest power. Then second entry with the space is 4, which is the constant value of the second highest power. And the last is the 25, which is the constant value, right? S power 0. So S power 2, then S power 1, then S power 0. So this is how you will explain to the MATLAB what your transfer function is. And once your transfer function is, since we want it to perform the partial fraction, so what we are dealing with the partial fraction is, let's say, what we get in the partial fraction, I'm writing the generic form, it is equals to the this, yeah. So what we are getting in the partial fraction is we have some direct terms, and then we have some residues and the poles in the as a result of the fractions value. So you will write it as k of s plus the first pole value divided by s minus first residue value divided by s minus first pole value plus second residue value divided by s minus second pole value plus third residue value divided by s minus third pole value, so on and so forth until you have the nth residue value divided by s minus nth pole value. So this is how you will arrange your results of the MATLAB to get the partial fraction form. So let's assume, just make a one complex partial fraction. Let's say you have output over input equals to s4 plus 8s cubed plus 16s square plus 9s plus 6, that's whole divided by s cubed plus 6s square plus 11s plus 6. So now I'm going to switch to the MATLAB and we will see how we are going to get the solution using the MATLAB. So that's the MATLAB interface. I'm not sure if you guys are aware with this software. Uh, so whenever you open a MATLAB, you have to create a new script, and before running the script, let's say you can create a new script from here. So now you are into the new. I already have a lot of scripts open which I can't shut down at the moment. So you have new scripts. You can name the scripts, or you once you are saving it, you can name as well. So before running it, you have to save it and make sure while you are saving, don't just write like, you can always go back, but if you write something here, um, you cannot go back and delete it. So so there are two different terms. One is called clear. Clear is any data that is generated in the MATLAB, it will clear all the data. And the other is CLC. It will clear all the commands that you have given to the MATLAB. So if you just click write CLC and press enter, it will clear everything. Right? But it's not going to clear from this editable script. You have to delete it yourself. So now let's start with the our transfer function. So this was our transfer function. Now we are going to write it into the MATLAB. So the first was always use the editable one, so that if you make a mistake, you can always edit it. Write num, that is numerator, equals to, and that's equals to 1 8 16, because I have written with myself 9 and 6, that's a numerator, and other thing is denominator, and that's equals to 1 6 11 6. If you add colon here, so the MATLAB won't repeat the same steps. It won't just re-show all these same thing which you have written above. It will just directly let you know the answer. But if you don't add the colon, it will show you again these terms and then show you the answer. Let's say once you've written this one, you can write as play. You see it has again showed me the same numerator and denominator. And yeah, just if I don't, let's again clear this one, clear the data. I will write clear, it will clear this generated data, and now I will write CLC, it will clear everything that was produced here, or the commands given. If I write colon here and again play it, so here you see I didn't see the commands again in this command window. I'm only seeing it stored in a workspace. So it depends upon you how do you want to work. Now I have informed the MATLAB that this is a transfer function I have, this is the fraction I have actually, and next is I want to find the residue and poles and the direct terms. So I there's a command for that, r and parenthesis numerator. You see it as red, they both are now colored blue, so it means MATLAB has recognized this function has been this term has been defined earlier, comma denominator. Now it has recognized the denominator as well. If it doesn't highlight like this, it means there's some mismatch between them, you have to check out. Otherwise it should highlight, and it lets you know that it has recognized these functions. Now I have given the command to the MATLAB that I want to find the residues, poles, and direct terms for this fraction. Now click run. You see now I have the pole residues, poles, and the direct terms. So this is R1, this is R2, this is R3, this is P1, P2, P3, that's K1 itself. Now how we are going to incorporate this one into our, how to write the partial fraction from here. I'm just copying this one. I hope it gets copied. Yeah. So from here, how you're going to write it, just recall the standard generic form of the partial fraction. That is k of s, that's a direct term. This one plus r1 divided by s minus v1 plus r2 and so on and so forth. So our partial fraction would become y of s over u of s. The first was k, and k has s exponent 0 and s exponent 1. So you always start with the right side and keep on increasing the power value. So to write the proper term, so it's s plus 2 simple. So the k is s plus 2, that was the first term, plus second term is r1 divided by s minus p1. So r1 is actually minus 6 divided by s minus p1. P1 here is minus 3, so minus minus plus, it's plus 3, plus that is r2 divided by s minus p2. R2 is minus 4 divided by s minus of p2, and p2 is minus 2, so it's minus minus plus, plus r3, it's 3 divided by s minus p3, and p3 is 1, so minus into the minus, that's plus, plus 1, and you can write it in a simple way, s plus 2 minus of 6 s plus 3 minus of 4 s plus 2 plus 3 s plus 1. That's This is how you can directly get the partial fraction from the MATLAB. It's quite easy. You can simplify it further. So s plus 2 minus of 2, that will become 3 divided by s plus 3, and you can add a minus of 2, it will become 2 divided by s plus 2 plus 3 into, sorry, 3 into 1 divided by s plus 1. So you see now you have these terms as same, and you can use that table of the Laplace transformation 1 over s, where is that, yeah, it's 1 over s into s plus a, or something like this one. So it will help you to simplify your solution. So only thing you have to do in the inverse Laplace transform is just try to get some fractions similar to the one you have in the table, so that you can directly transform that into the time domain. So this is how you can perform the Laplace transform of transformation of partial fraction of a system, and find the transfer function and perform the partial fraction using the MATLAB. So the next we can do is we can deal with the second order systems. So let's assume we have a system here. That's an example 2. Let's assume we have a system, mass spring damper system, and then we have a damper here, and it's connected in series with the, it's better not to define now, with another spring. So let's call it K1, let's call it K2, let's call it, oh, let's call it B2, or you can call it that's just as B. Now, since these two elements are in series, and we know that they are in series, so they are not going to be displaced by the equal amount. There will be some kind of a relative displacement between them. So to accommodate that one, we have to define another node between them. So that's another coordinate here we have. Let's call it y, and we have a coordinate for this mass, that's x. So, and we have seen this in the first lecture. So now consider this mechanical system and consider it is initially at the rest. So our position at time 0 0, and at velocity at time 0 is also equal to 0. And suppose that the force that is being applied is a step force. So it was applied with a step force. If you remember the step force, that's a unit. So let's say if the force this one, so you'll just write the, okay, Laplace transformation of this force would be equal to 1 over s, whatever the step force they mentioned you, the Laplace transformation of that step force would be 1 over s, unless they mention that the step force of magnitude 10, so it will be multiplied by 10, it will be 10 over s. So this is how you write the Laplace transformation of the step force. So going back to our lecture, yeah. So now we have a system that has been excited by the step force and as an input, and we have to determine the displacement as an output, and the displacement output we are interested in is x of t, this one, and obtain the transfer function of this system, that is g of s, if the mass of our system is of the mass is 0.1 kilogram and the damping is 0.4 newton second per meter, and k1 is equals to 6 newton per meter, and k2 is equals to 4 newton per meter. And yeah, assume that the step force has a magnitude of 10. So the magnitude of step force is 10 newtons. Now we have to obtain the analytical solution x of t. We have to find the time domain solution x of t for this system. So first of all, we have to make a free body diagram for this system. So let's say if this is our mass, and if the step force is applied in this direction, and let's assume that this is the positive direction and that is a negative direction, and the force is applied downwards in the positive direction, and the system obviously starts to move downwards. So it will be opposed by the k1 fk1, and it will be also opposed by the second spring force, that's fk2 or fs2, whatever you want to call. And if system is moving in this direction, so naturally its inertia will be acting in the opposite direction as well. So we have mx double dot in the opposite direction as well. Let's call it this p. So you can write this one, and since yeah, for fk2, since this is the, we have the y here as well, y coordinate as well, so it's not just moving absolutely, there's some relative motion for the second spring. So and if you draw the free body diagram for this node, since fk2 is acting in this direction for here, so for the Newton's third law it will be acting in the opposite direction for this one, and if it is acting in this direction for this one, the damping force will be acting in the opposite direction fb2. So here it shows that the spring force, second spring force equals to the damping force, so we can write the first equation as k2 x minus y equals to b2, oh sorry, by dot, that's a by dot, that's the first derivative, and our another equation will be mx double dot plus k1x. I'm just simplifying it directly. You can write it as negative and then take on the other side and turn it to positive, plus k2 x minus y, that's whole equals to the p, that's a step force. Now we have to take the Laplace transform for these equations. Let's call this equation 1, let's call this as equation 2, and taking the Laplace transformation, taking Laplace transform, forming Laplace transform of equation 1 and 2. So the 1 will become k2 x of s equals to, if we just simplify this one, just again going to write it again, k2, yeah. So it will become k2 x of s minus k2 y of s equals to b s y of s. It will become, now you can segregate the xs and y of s, so it will become k2 x of s equals to k2 plus bs into y of s. So that's our new equation. Let's call it equation number 3. And for equation number 2, we can perform the Laplace transformation, and it will give us ms square. I'm going to write it directly, k1 plus k2. You can simplify yourself, into x of s equals to k2 y of s plus p of s. So now we can, because our main purpose is the input is the step force p while the output is x of t, so we are not concerned with the y, we are concerned with this output x. So from this equation you can eliminate the y, so that we have only x and p in our equation, so we can find the ratio between them to get the transfer function. So we know y of s equals to k2 x of s divided by k2 by b2s, so we can substitute that in equation 4. Now substituting equation 3 in 4, so we will have ms square plus k1 plus k2 x of s equals to, that will be k2 into this k2, that will be k2 square, divided by k2 plus bs x of s plus p of s. Now we have eliminated the ys in our system, in our equation. We don't need it anymore. Now what is a transfer function? That is a Laplace transform output over input. So we know the output is x of s, the input is p of s. So first segregate them and then we can make the ratio. So take this on the other side, so we can arrange it like ms square plus k1 plus k2 minus k2 square over k2 plus bs into x of s equals. So this is what we have, and now what we can do is take common as x of s, and it will become, and you have to multiply this on the other side, it will become ms square plus k1 plus k2 into k2 plus bs minus of k2 square equals to, and you can take the denominator on the other side. I'm doing these steps directly. I hope you are following with the maths, into p of s. So now we can find the Laplace transform output over input, so it will become x of s over p of s, equals to uh, bs divided by k2 whole divided by, uh, if you wanna simplify it even further, it will become m k2 s square. Yeah, m k2 s square plus k1 k2 plus k2 square plus m b s cube plus k1 bs plus k2 bs minus k2 square. So this is what we have, and we know we can cancel out this one and this one, and what we have is just arrange it with the higher terms. With respect to the highest terms, x of s divided by p of s equal to bs plus k2 divided by m b s cube. Then the next second highest term is s square, highest terms of the s complex variable, plus m k2 s square. Then we have s here plus k1b plus k2b into s and plus k1 k2. So this is what the transfer function we have for our system. Next is we can plug in the values of the mass, spring and damper. So we will be left with 0.4 s plus 4 divided by m into b s cube, that makes 0.04 s cube, plus m into k2, that makes 0.4 s square, plus k1b plus k2b, it becomes 4s, plus k1 into k2 is 24. uh, so this is what you have here. You can take 0.4 as common, or you can simplify it further. So you can take the 0.04 as common from the denominator, x of s over p of s. So it will be, because we want to linearize this part, 0.04, it becomes s cube, plus it becomes 10 s squared, plus that's 100 times more, that's 100s, and plus that makes up uh, to 600 for this one. And you can take 4 common from 0.04 common out of this one as well in the numerator. So in the original 4, it will become 10s plus 100. So they will cancel out each other. So now what you have is, we are just doing it to linearize our equation, don't have the constant value with the highest variable, highest power variable. So it becomes 10s plus 100 divided by s cube plus 10s square plus 100s plus 600. Now we can substitute this one, because what we were interested in, we were interested in to find that displacement x of s, or the x of t, sorry. So x of s will be equals to 10s plus 100 divided by s cube plus 10s square plus 100s plus 600, and p of s, and it's actually one, it's a step force, so its Laplace transformation is 1 over s, and since the magnitude of the step force was 10, so multiply by 10, so you'll write it as 10 over s. We have taken the p of s on the other side, it will be multiplied by 10 by s. So this is what we have here. What we can do is just multiply this 10 and s. It will be 100 s plus 1000 divided by s power 4 plus 10 s cube plus 100 s square plus 600 s. So this is what we have in our uh, numerator and denominator. So what we have to do is, I want to convert that back into the time domain to get the displacement. Obviously that's a time domain thing, and for that I need to perform the inverse Laplace transform in this inverse Laplace transformation of this expression. And for the inverse Laplace transformation, we need to perform the partial fraction to get the simple fractions, and then use the table to convert that into the time domain. So again, now we need a partial fraction, so we will performing that using the MATLAB. So jumping back to the MATLAB, first of all, clear all the workspace, and then write CLC. So you have cleared everything. You can, that's editable one. You can remove this. You don't need to remove this because we are going to use this command anyhow. So our expression is, in numerator is 100, 1000 is the constant value, then the first power is 100. So we don't need all of these values. So first is 100 and second is 1000. So we start counting from right side, 0, 1, 2, 3, 4, so on and so forth. And denominator is 0 for the constant value, then the first power has 600, then 100, then 10, then 1. So we have actually 0 for the constant value, then 600 for the s, and then 100 for the s square, I guess, yeah, and then 10 for the s cube, 10 for the s cube. We have one more, that is exponent power 4. So it's 0, 600 s, 100 s square, 10 s, 1 s power 4. 0, 600 s plus 100 s square plus 10 s cube plus 1 exponent 1s exponent 4. So we have defined the numerator and the denominator. All we need is a residue, poles, and the abstract, the absolute values, direct terms. So just select play or run. Now it has calculated the transfer functions for you. Now you have the complex numbers here, and you don't have any direct terms. So I'm just copying that so that we can write it in the fraction form. Copy from here and write on this side. So from here you can write the partial fraction for this one as x of s. The first was k of s, that is nothing, there is no k of s. Second one was r1 divided by s minus p1. So r1 is minus this divided by s minus of this one. So it will be minus 0.6845 plus 0.2233 iota. I'm just writing it roughly. 0. Sorry, 2233 iota divided by s minus p1, which is minus 1.28974. You can just take minus as common, so it becomes plus, and it will be 1.2898 minus 8.899 iota, plus that is r2 divided by s minus p2. So it will become minus 0.6845 minus 0.2233 iota. It's minus, right? And it's whole divided by s minus p2. S minus p2, p2 is minus of 1 point. Again, take the minus as common, it will become plus, and 1.2898 plus 8.899 iota. That's the second term. The third, because you have four terms in the partial fraction, I'm writing it here. Then plus r3 divided by s minus p3, that is minus 0.2977 plus 0.00 iota. We don't have any ideal number here. Divide by s minus p3. So s minus minus plus, that is 7.4204 plus r4 divided by s minus p4. So r4 is 1.6667, and that's just an iota, divided by s minus p4, and p4 is 0 actually, so it's simply s. So that's our partial fraction after the uh, using MATLAB. So now what you can do is perform the inverse Laplace transformation of this one and let me know the final answer. So that's your kind of homework. You know, the next step, all you have to do is play with some mathematics and try to match numbers in that table. This one, try to match the fraction in these tables and then try to solve it. So that's for the inverse Laplace transformation, and this is how we can use the MATLAB to perform the Laplace transformation. Now the next part we are going to study is the uh, finding the response of a system. Now we have seen how we can get to the final solution using the Laplace transformation and how we can use the MATLAB to aid our solution. Now we are going to use the MATLAB for finding the solution of our system, that is those nice plots, how system is changing its position or response with the time. So this is what our next target is. Let's assume we have a system that has now now let's jump towards studying the transient response of our systems using the MATLAB. So currently we are going to deal with the time domain input, such as the step input or the ramp input or the impulse input, because they are dependent on time. So we are going to use those to study the Trojan response of our systems. In the next chapter, the next topic, we are going to study the frequency domain inputs like the sinusoidal input, sinusoidal excitation. And for that, we have a separate kind of a transfer function called the sinusoidal transfer function, as I have mentioned in the beginning. So we are going to look into that one in the next lecture or the next section. So let's make another page for our. So let's say transient response. Although you can do it manually as well, but it will take a lot of time. You have to take the readings for each and every second. You can derive the final equation x of t after the inverse Laplace transformation. Let's say 1.5 e exponent t plus 5.2 e exponent 2t xyz. You can keep on substituting the value of t equal to 0, 1, 2, 3, and find out the values of x of t. But the MATLAB will do it for you. You don't have to invest your time into this one, into this manual calculation. So let's suppose if we have a transfer function y of s divided by x of s, that's let's say 2s plus 25, and the denominator is s square plus 4s plus 25. So this is a transfer function. If you draw a block diagram, if you have studied the control theory before, so this is how the MATLAB reads the transfer function. You supply the input, it will process it, and it will let you know the output, right? So if you give the input, and it will have the transfer function of your system, using that transfer function, MATLAB will let you know the output. So how to tell the MATLAB that this is a transfer function? We have seen that how to define this fraction, but telling the MATLAB this fraction is actually a transfer function of any system. So for that, we define the system using a command sys equals to tf, that is transfer function. And what the transfer function is, it is simply that numerator and denominator value that we have mentioned to the MATLAB. So that's how MATLAB will MATLAB will read that, okay, this numerator and the denominator values that you have provided are actually the transfer function of any system. So once you have it, it will show you the transfer function, and then you can use different kinds of input. Let's say we are going to start with the step input, step response, you can say. So what is a step response in essence? So a step response is, let's say this is the zero line, that's the time. So you don't have any force, only at particular interval of time. Let's say 1 second you applied a force of any magnitude, let's say 5, and then you maintain that force. So that's kind of a step. That's called a step force. If it is impulse force, so it was let's say 0 force, this is 5 Newton, and that's a timeline. So at any time interval, let's time instant 1, let's say 1 second, sorry, not t, 1 second, you applied an impulse force for a very short duration of time, and then it was removed. So for the step response, if you apply the step force onto a system, maybe the system response is like it got excited in the beginning, and then after some time it maintained the certain value of displacement. Let's say this is x of t. But for the impulse one, let's say this is the zero line here, this is zero line, this is any value, let's say 10, here this zero lines. For the impulse one, it will be excited for some time, and it will slowly get back to its zero line because the force has been removed. It will the energy will damp out. But here you are maintaining that force value, so there will be after some time there will be a steady state at a constant magnitude of displacement. Here there will be a steady state by returning of the system by in that case system returns to its neutral position or zero position, you can say. So let's say if you're applying the step force to your system in the MATLAB, you will just give the command to the MATLAB step step to this system, or you can write it as step to that numerator and the denominator value, which is actually the transfer function of your system. So once you give that command, you define, first of all you define the numerator and denominator, then you give tells the MATLAB that this numerator and denominator are actually the transfer function of our system. Then you apply this force, step force, like this. And so that in that case MATLAB will compute itself the time interval and the total time of the study, let's say. So like for how many seconds you want us to see the response of a system, and what should be the data point concentration, like after, let's say after every 0.1 second you want a reading. So MATLAB will decide it's on its own. But if you want to give these by yourself, you have a particular requirement of time interval that you want to study the system after every 1 second, after every 2 seconds. So you have to define the time interval to the MATLAB as well, and we'll look into that later. So let's jump to the MATLAB and check out. Again, just clear all the workspace and press CLC. You have cleared everything. Remove this thing from editable window. So first of all, let's say we have a transfer function that is a numerator equals. So I'm going to write it directly. That is numerator equals 2 or 20 and 10. Uh, divide by, sorry, and we have a denominator equals to 1, 2 and 10. So this is our numerator and denominator. Let's say I'm just on a side note, it's not a part of our course. If you wanna make a new section, because you don't want to run whole program again and again, you have already defined the value of numerator and denominator. Okay, just write it as denominator d and e. Yeah, you see it is saving it again and again, not to save it as a new variable. So you can always delete this one. Yeah. Uh, Now I want to give other commands, but I don't want MATLAB to waste time in again calculating or following these commands. So what you can do, you can enter the percentage sign twice. Now it has created a new section. And instead of running the whole program, you can just run section. So here I will tell the MATLAB that this numerator and denominator are actually the transfer function. So I can write it as SYS, that is system, equals to, we have the trans SYS, and just click OK, or you can just run the section. Now it is running those values, or maybe you can just stop at the moment, write the grid command as well, and then run the section. Now MATLAB has defined its own time metrics, so it knows what should be the total time duration and what should be the time interval for each reading. So now we have this response plot of our system. Since it was a unit step force, and so we have the amplitude, it was excited in the beginning, that's a transient region of the response, and now it has reached a steady state, and you see it as maintaining the amplitude of 1 because it's a unit step force, that the amplitude of the step force is 1, so it will maintain it, as we have seen that it's in the step force, it maintains the force is still there, you're continuously applying that force. So this is how you can find the response of a system using the MATLAB. So let's define the time interval ourselves as well. So if I go back to the MATLAB here, and let's say I wanna define the time interval as well. So we will write it as system, comma. Now again consider the same example that we have seen in the earlier in this lecture. Yeah, this system. So let's start with this system. So I'm going to write its transfer function, that was x over s divided by p of s, and it was equals to b2s plus k2 divided by mb2s cube plus mk2 s square. We have written this earlier, so I hope you have this transfer function k1 k. This was our transfer function that was output over the unit step input force with the 10 magnitude. And but if we recall, that system has additional coordinate here because the damper and the spring were uh, connected in series. So that was y, sorry, y, and this was x. uh, let's suppose if we wanna study the displacement at both the coordinates based on the applied input load, let's say in our case is step force p. So we can do that as well in using the MATLAB, because previously we have just studied the x of s, we eliminated the y of s. So we can simplify the same equation. If you, I'm just going to write it directly. You can do it yourself in your free time. So here, what we did in equation 3 and 4, we eliminated the y. We substituted y in terms of x. What you can do is you can substitute x in terms of y in this equation, and then find the y of s over p of s. Just do the inverse in this one. So if you just do that, you will have the transfer function of output y based on the input p of s. Sorry, you will have the transfer function of output y of s divided based on the input p of s equals to k2 divided by b2s plus k2. So now we have both the sorry, not this one, it's on x of s. And then you can substitute that one into the other equation. But anyhow, the final form would be y of s divided by p of s. It will be equals to k2 whole divided by mb2 mb s cube plus mk2 s square plus k1 plus k2 bs plus k1 k2. So this or what we have. So that's y over s, and that's other one is x s over ps. So now we can solve for both of them. If we have solved for the first one, if we solve for the second one, it will become 4 divided by uh, 0.04 plus 0.4 s square. If you substitute the same values, plus 4s plus 24. I hope you have all those values. You can always rewind and check out the values, and you can simplify it further. It will become 100 divided by s cube plus 10 s square plus 100 s plus 600 y of s over p of s. And since our step force was 10 in magnitude, and we are keeping it in the Laplace domain as well. Let's say the P of t was equals to 10 of unit step force. 10 times of unit step force, so that's 10 magnitude of step force. So you can rewrite this transfer function as ui of s over u of s equals to and just multiply by 1000 divided by s cube. The denominator remains same, s square plus 100 s plus 600. And for x of s over p of s, sorry, it will become x of s over u of s equals to, that is 100s plus 1000 whole divided by uh, s cube plus 10s square plus 100s plus 600. So this is what we have for both the cases. Now what I want to do, we want to study the transient response for based on both of these independent coordinates. I just don't want to study x of s only. I also want to study the displacement at the y at that node, which is an independent coordinate of y of s. Now you can substitute both of them in the MATLAB and you can find out. So let's check out. Yeah, we have both transfer functions. Let's check out. In this case, close this one. Start with here. So first of all, you may